Synthetic Routes, OCR Chemistry A, 6.2.5, Parts B and C. We will consider two-stage routes, firstly for aliphatics and then aromatics, move on to multiple functional groups and then multi-stage synthetic routes. So the setup is I will identify a starting molecule and a target molecule. Your task is to suggest an intermediate molecule and the reagents and conditions required to convert stage 1 and for the conversion stage 2. Pause the lesson and write out your solutions. Okay, so I am about to reveal my answers. So my solution is to form propene from propan 1-ol by dehydration with concentrated sulfuric acid and heat, and then add a water molecule in the form of steam in the presence of the catalyst concentrated phosphoric acid to form, by Markovnikov's rule, propan 2-ol. Right, let's move on to the second problem. Starting with propan 1-ol, how could we form 1,2-dibromopropane in 2 stages? Pause, solve the problem, come back to check against my answer. Okay, I am about to reveal. Once again, I'm going to dehydrate propan 1-ol into propene, but rather than adding water as in problem 1, I'm going to add bromine, Br2, at room temperature to form 1,2-dibromopropane. Correct your solution if you haven't followed that pathway. Okay, let's move on to problem number 3. Again, starting with propan 1-ol, how can we form 2-bromopropane? Pause, write your own solution, come back to check. Okay, I'm about to reveal my answer. So again, I'm going to dehydrate with concentrated sulfuric acid heat. I've added the detail of under reflux to form propene. And I'm going to add hydrogen and bromine atoms in the form of hydrogen bromide at room temperature and pressure to form 2-bromopropane. Correct your work. Let's move on to problem number 4. So starting with propene, our target molecule is propanone. Pause, come up with an intermediate and the reagents for stage 1 and stage 2. Check your answer when you are ready. Okay, I'm about to reveal. So to propene, I'm going to add water H2O across the double bond. So the conditions are steam and catalyst concentrated phosphoric acid will make me propan 2-ol. I then oxidize propan 2-ol with sodium or potassium dichromate, dilute sulfuric acid and reflux to form the ketone. Now this is a good example of how these synthetic pathways may best be solved by starting with the target molecule. The question might be, okay, propanone is my target. From which molecules can propanone be made? Well, there's only one in the OCR specification, and that is propan 2-ol. So if we then know we've got to make propan 2-ol, we know that we convert propene into propan-2-ol. So a useful technique or a common technique in solving the problems of synthetic pathways is to start with the target molecule and work backwards. Let's move on to problem number 5. So number 5, bromoethane to the target molecule ethanoic acid. Think it through, come up with a solution, come back to check when you are ready. Okay, so I am about to reveal. So bromoethane to ethanoic acid. Well, from what molecule could we make ethanoic acid? Well, ethanol would be a prime candidate, especially as we're starting with bromoethane. So ethanol can be oxidized with sodium dichromate, dilute sulfuric acid, heat under reflux to ethanoic acid. And bromoethane can be converted into ethanol using dilute sodium hydroxide and heat under reflux. So correct your work and then move on to problem number 6. So number 6, propan-1-ol to butane nitrile. Now you need to correctly identify the target molecule. So let's just make sure we've got the structure of butane nitrile. So it's 3 carbons and then the nitrile group. So there is butane nitrile. So propan-1-ol, just in shorthand, is like so. So how can we convert propan-1-ol to butane nitrile? Pause, write out a solution and come back to check against mine. Okay, I'm about to reveal. So butane nitrile can be formed from 1-bromopropane. By a substitution reaction, the cyanide ion will replace the bromine atom within the molecule. So KCN in ethanol will go to butane nitrile, as drawn on the previous slide. Then we need to convert propan-1-ol to 1-bromopropane, sodium bromide, concentrated sulfuric acid. So that's the formation of a haloalkane from an alcohol, sodium bromide, for example, and concentrated sulfuric acid. Okay, let's move on to problem number 7. So 1-bromopropane to propene in 2 stages. Think it through, take your time, write your solution, come back to check when you are ready. Okay, I am about to reveal. So propene can be readily made from propan-1-ol by dehydration, concentrated sulfuric acid, heat under reflux. We've met that in this lesson before. And 1-bromopropane can be converted into propan-1-ol, reaction of dilute sodium hydroxide, heat under reflux. So that is how that conversion would take place in 2 steps. By the way, it is possible to do it in 1 step, but the reaction is not on the OCR Chemistry A specification. So this is a pathway that would be expected in OCR Chemistry A. Let's move on to problem number 9. Of course, I meant problem number 8. Propene to form a mixture of bromoalkanes, not strictly a synthetic pathway, but See how you get on with it. Pause, write out a solution, and come back to check against mine when you're ready. Okay, so I'm about to reveal. So a mixture of bromoalkanes really indicates it's the bromination of an alkane. So propane, bromine, ultraviolet light, you get a mixture of bromoalkanes. I thought I'd throw that in for review purposes. How do we go from propene to propane? Well, again, a reaction that sometimes slips under the radar of A-level students. Hydrogen, nickel catalyst, 150 Celsius, adding hydrogen across the propene carbon-carbon double bond. Okay, so now let's move on to problem number 9. Propene to the target, 2-aminopropane. Think it through, take your time, research if necessary. I should have said that earlier on the lesson. Come back when you're ready to check your answer. Okay, I'm about to reveal mine. One important point is that our starting molecule has a 3-carbon chain and our target molecule has a 3-carbon chain. So to make 2-aminopropane, we could come from 2-bromopropane, excess ammonia, NH3 in ethanol. You need to know the reagents and conditions. And propene can readily be converted into 2-bromopropane following Markovnikov's rule, HBr, room temperature and pressure. Okay, let's try problem number 10. So our target is polypropene, bit of a clue in the name, I hope, from propan-2-ol. Try it, come back to check when you are ready. Okay, I am about to reveal. Well, I hope it's obvious that the intermediate molecule to make polypropene must be propene. The specification doesn't actually give reagents and conditions, nor does the textbook, but generally high pressure and temperature will do it. So how do we get propene from propan-2-ol? Again, a reaction met earlier in the lesson, concentrated sulfuric acid, heat under reflux. So let's now move on to 11. 1-bromopropane to butylamine. Make sure you know the structure of butylamine. Pause, come up with a solution, check when you are ready. Okay, so I am about to reveal. The key point here is that bromopropane has 1-bromopropane has 1, 2, 3 carbons in its chain, whereas butylamine bit rough and ready, but has got 4. So we need to add a carbon to the carbon chain. So that is one of the most important reactions of the haloalkanes. Substitution of the bromine for the nitrile group, KCN in ethanol, will give us, oops, can't count numbers of bonds, butane nitrile. So this now has got 4 carbons, 1, 2, 3, 4 in the chain, and then we reduce the nitrile group, hydrogen and a nickel catalyst, so we're adding hydrogens to both the carbon and to the nitrogen. So there is our solution. Okay, let's move on to number 12. 1-bromopropane to form butanoic acid. Again, please note we've got 4 carbons in the carbon skeleton for the target and only 3 carbons in the starting molecule. That's a key point to observe. Okay, come up with a solution. Check your answer when you have thought it through. Okay, I am about to reveal. So 1-bromopropane to butane nitrile, we need to add a carbon to the carbon skeleton. So KCN in ethanol is the most useful reaction of haloalkanes or bromoalkanes. And then a reaction we haven't mentioned yet today is the hydrolysis of the nitrile group. Dilute hydrochloric acid, heat under reflux will form butanoic acid. Correct your work and then move on to number 13. So propane nitrile to form propanoyl chloride. Think it through. Come back, check your answer when you're ready. Okay, so I am going to reveal. So to make propanoyl chloride, the most likely pre-molecule or intermediate is propanoic acid, which reacts with thionyl chloride to make propanoyl chloride. I may just remind you of the structure of propanoyl chloride. And of course, propanoic acid comes from propane nitrile by hydrolysis, dilute sulfuric acid or dilute hydrochloric acid, heat under reflux. Okay, so moving on to 14. Propane nitrile to ethyl propanoate. So this, to be clear, is an ester. Propane nitrile to ethyl propanoate. Pause, come up with a solution, return to check your answer when you are ready. Okay, so I am going to reveal. Okay, so propane nitrile to propanoic acid, and then propanoic acid reacts with ethanol, concentrated sulfuric acid catalyst to ethyl propanoate. Now, if that causes any problems, you probably need to draw the structure of the product. So there is ethyl propanoate. So we're going to make propanoic acid. This is the chain of the propanoic acid, and then we're adding on the chain of the carbon skeleton of the alcohol, so ethyl propanoate. Let's move on to number 15. Propan-2-ol to 2-hydroxy-2-methyl propane nitrile. It might be the best tactic here to draw the structure of the target molecule and work backwards. It's quite simple from there. Have a go. Come back to check when you are ready. So I'm going to reveal. So here is 2-hydroxy 2-methyl propane nitrile, and that is produced by the addition of hydrogen cyanide to propanone. The reagents are sodium cyanide and hydrochloric acid, dilute hydrochloric acid. So propan 2-ol to propanone is oxidation, potassium dichromate, dilute sulfuric acid, heat under reflux. So there are the solutions to our first 15 problems. Well, there seems to be one more two-stage aliphatic pathway. So 16, propanone to 2-bromopropane in 2 stages. Think it through, write your solution, come back to check when you are ready. Okay, so I am going to reveal. So propanone reduced to propan 2-ol. The reagent is sodium borohydride, then water. Having made propan 2-ol, we can then substitute bromine for the hydroxy group. So sodium bromide, concentrated sulfuric acid, heat under reflux are the reagents and conditions. Okay. So that is now 16 aliphatic pathways that we have looked at. We're going to move on now to the next area to look at, which is, of course, 2-stage aromatic routes. So let's start with some pathways derived from benzene. So benzene in 2 stages to phenylamine or phenylamine. Okay, have a go, come back when you are ready. All right, so I am about to reveal. So phenylamine must come from nitrobenzene, so going from the target backwards, and that conversion from nitrobenzene to phenylamine is tin, concentrated hydrochloric acid, followed by excess sodium hydroxide to form nitrobenzene. From benzene, it's the nitrating mixture, concentrated nitric acid, concentrated sulfuric acid, 50 degrees Celsius and reflux. Okay, let's go on to number 18. Starting with phenol, 2 steps to achieve a mixture of 2-aminophenol and 4-aminophenol. Pause, come up with a solution and then restart to check. Okay, I am going to reveal. So phenol is activated compared to benzene, so the conditions for nitration will simply be dilute nitric acid, room temperature and pressure, and the hydroxyl group is 2,4-directing, so we have a mixture of 2-nitrophenol and 4-nitrophenol as our intermediate. Reduction of the nitro group to the amine, so we get a mixture of 2-amino and 4-aminophenol. Okay, so number 19. So let's try benzene to 1-phenyl ethanol. So the first thing you need to do really is to get the structure of 1-phenyl ethanol correct. So here's a structure for ethanol. So this is carbon number 1. Because the side chain attached to the benzene ring has a functional group, we name the benzene structure as phenyl attached to carbon number 1. So that's 1-phenyl ethanol. Okay, so come up with a solution how to make 1-phenylethanol from benzene. Okay, I'm going to reveal. So phenylethanol was indeed a secondary alcohol, so that will come from a ketone. So phenylethanone. Again, here's ethanone, and because the side chain contains a functional group, the benzene ring is named as phenyl. So phenylethanone. So phenylethanone to phenylethanol is sodium borohydride. How do we get phenylethanone? This is a Friedel-Crafts acylation. So ethanoyl chloride, aluminium trichloride catalyst. Correct your work. And when you're ready, let's move on to number 20. So number 20, nitrobenzene to 4-nitrophenylamine. Now you have to think about the position of the further substitution here. Okay, think it through. Come back to check your answer when you're ready. Okay, I'm going to reveal. So a key point here is that the amine group is 2,4-directing. So if we draw the amine here, phenylamine, then further substitution will occur at carbon number 2 or position number 2 or position number 4. The amine group is 2,4-directing. So our first step here is to turn nitrobenzene into phenylamine with tin and concentrated hydrochloric acid, and then to nitrate phenylamine. Dilute nitric acid will do the job. So we get 4-nitrophenylamine. We'll actually get a mixture of 2-nitro and 4-nitro, but I seem to have just gone for one target molecule here. Okay, so let's move on to 21. Benzene to 3-bromo-nitrobenzene. Again, this position of further substitution has to be taken into account. Think it through carefully, come up with a solution, come back to check against mine. Okay, so I'm going to reveal. The first step is to nitrate the benzene ring. So concentrated nitric acid, concentrated sulfuric acid, 50 degrees Celsius, heat under reflux. The reason I'm concerned to nitrate initially is because the nitro group is 3-directing. It's deactivating and 3-directing, so the positions of further substitution will be on carbon number 3 in the benzene ring. So we then brominate with bromine and catalyst aluminium tribromide, and the substitution would be at position number 3. So 3-bromo nitrobenzene is the solution. Okay, so let's move on. So we should now consider synthetic pathways where the starting molecule, or indeed the target molecule, has multiple functional groups. So let's consider the amino acid serine. Now serine contains 3 different functional groups. We've got the amine, we have the primary alcohol group, and of course here we have the carboxylic acid. Now, as these are separated by the carbon skeleton, these functional groups do not interact to affect property. So each functional group displays its typical properties. So within this amino acid, serine, we have the reactions of an amine, the reactions of a carboxylic acid, and the reactions of a primary alcohol. So to reinforce the idea, I'd like you to look at the molecular structure below. Aspartame, it's a sweetener. Could you identify the functional groups? Pause, think it through, come back to check your answers when you are ready. Okay, so I'm going to reveal. We have, of course, the carboxylic acid. We have an amide. The amide, that's in fact a secondary amide, but we have an amide. We have an amine. We have an ester. And let's not forget, we've also got a benzene ring. So within aspartame, we've got 5 different functional groups, all of which will show their particular reactions. Okay, so having looked at multiple functional groups and at two-stage aliphatic and aromatic routes, we need to move on to the complexity of multi-stage synthetic routes, that is 3, 4, 5-stage synthetic routes that may or may not involve more than one functional group. So here is a multi-step synthesis. Butane dioic acid synthesized from ethene. So there's our starting molecule, and butane dioic acid is our target molecule through a 3-stage process or conversion. Pause, think this through very carefully, come up with these following items. Draw and name the structure of compound A. State the reagents for stage 2, which is a substitution reaction. Draw the structure of compound B. State the reagents and conditions for stage 3. Classify the types of reaction in stage 1 and stage 3. So stage 1 and stage 3. So this is very similar to the type of thing you would get in an exam paper. Okay, so pause, work your way carefully through this and come back to check your answers when you have done your very best. Okay, so if you are ready, I am going to reveal some answers. Firstly, there is 1,2-dibromoethane. So we're adding bromine across the carbon-carbon double bond to give us 1,2-dibromoethane. Stage 2 is a substitution reaction, so it's that very important reaction of haloalkanes. We're going to substitute for the bromine with a nitrile group. So you'll notice we go from 2 carbons here to 4 carbons. That's absolutely typical. We've increased the carbon chain length by 2 carbons, so 2 nitrile groups. So compound B, whoops, I've forgotten to answer the question, what are the reagents? KCN in ethanol. Then compound B, we've substituted the nitrile group for bromines twice. Then what are the conditions? We're going from the nitrile group to the dioic acid. Well, that's hydrolysis. Dilute hydrochloric acid, heat under reflux. and classify the types of reactions, stage 1 and stage 3. Well, I've already said stage 3 is a hydrolysis, and stage 1, well, that is an electrophilic addition. Okay, so let's move on to a second example. So this time we have a synthetic route outlined, benzene to phenyl ethanone to, if you remember, 1-phenyl ethanol, and then to, well, this is styrene, phenyl ethene. State the reactants and conditions for each stage. Pause, write down the reactants and conditions, and come back to check your answer when you are ready. Okay, so I'm going to reveal ethanoyl chloride and catalyst aluminium trichloride. Then this is obviously a reduction, sodium borohydride, then water. And here this is a dehydration, concentrated sulfuric acid, heat and reflux. Okay, let's move on. Okay, so problem number 3, the N-substituted amide C6H13NO can be formed from butan-2-one in 4 steps. So here they are. Here is butanone, and here is the N-substituted amide. 4 steps, 1, 2, 3, 4. State the reactants and conditions required for each step. Draw the structure of the products. State the mechanisms for steps 1 and 3. So you do need to identify what's meant by the N-substituted amide. Bearing in mind we're starting with butanone. Okay, think it through, take your time. It may take you a little while to work there, but when you're ready, come back to check your answers. Okay, so I'm going to reveal. So C4H10O from butanone, we're going to make a secondary alcohol. So that's sodium borohydride and water, that's nucleophilic addition. Then having made the alcohol, of course, we can go to the bromoalkane, sodium bromide and concentrated sulfuric acid. Having done that, we can go to the amine. So we're substituting the NH2, the amine group, for the bromine atom. We haven't mentioned this before in this lesson, but this is ammonia in ethanol. This is nucleophilic substitution. Then having created the amine, we then are going to make the N-substituted amide. So reaction with ethanoyl chloride, and you can see that that is the amide being formed by a condensation reaction. So let's look at problem number 4. Synthesize N-methylethanamide from chloroethane in 4 stages, stating the reactants and conditions and drawing the structures of the intermediate molecules. So let's start with chloroethane, and let's draw our final product, N-methylethanamide. And we'll put in the 1, 2, 3, 4 stages required. Now I'm going to work backwards here myself, and I suggest that you do. But before I reveal my answers, pause, see whether you can come up with the 3 intermediate molecules and the 4 reactants and conditions required. Come back when you are ready to check against mine. Okay, so I'm going to reveal my first thoughts, which are to make the amide, we must have in the OCR A specification an acyl chloride, so ethanoyl chloride. And those acyl chlorides react with primary amines to make a secondary amide, an N-substituted amide. So methylamine at room temperature with ethanol chloride being the intermediate molecule. Now, from what type of molecules can we make acyl chlorides? That's carboxylic acids. So that would be ethanoic acid. And the reactant to carry out that conversion is thionyl chloride. Ethanoic acid comes from ethanol, standard oxidation mixtures, heat under reflux, and of course haloalkane to alcohol, dilute sodium hydroxide, heat under reflux. So before moving on to the summary questions, in this particular case, I recommend going through this lesson once again so that you become fully fluent in identifying the reactants and conditions needed for each of the conversions involved. When you are fully fluent, you are then in a position to solve problems, and I recommend that you then move on to the summary questions, page 503, if you have the OCR endorsed textbook to hand. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.